Okay, so where else are we going to use our complex numbers? Well, we're going to use them to help us solve polynomials that have complex roots. So we've already seen a kind of example of this where we might ask you to solve something like z squared plus 2z plus 5 equals 0. So we can see that taking the form of a quadratic. Okay, you can also see why I put lines from z's, because if I didn't, that would look very similar. So again, we used it as one of our examples at the start. We can chuck this into our quadratic formula. Minus 2 plus or minus the square root of 2 squares minus 4 times 1 times 5 all over 2. That's going to give me minus 2 plus or minus the square root minus 16 over 2. And this then is where I'm getting on to z is equal to minus 2 plus 4i over 2, or minus 2 minus 4i over 2 equals minus 1 plus 2i, and here we've got minus 1 minus 2i. Okay, so again, I've shown that I can find the roots. I can just use my equation, easy. All right. What we might want to do though is we might want to ask you to do something a little bit more complicated. So to part A, we're going to show that z equals 1 plus 3i is a root of the equation 2z to the 4 minus 3z cubed plus 17z squared plus 12z minus 10 equals 0. And then part B, I'm going to find the remaining roots. Okay, now one of the advantages we've got when we're doing this, and we've just seen it happen up here, is that if we can find one of the roots, we also know that its conjugate is a root. So remember, that's where we change the symbol for it. So here we had a plus ib and a minus ib. Okay, that's what we're looking at as our conjugates. So minus 1 plus 2i and minus 1 minus 2i. So the first part, we're going to have to show that 1 plus 3i is a root of the equation. So what we're going to do is we're going to have to substitute this in. So we've got two lots of 1 plus 3i 4 minus 3 lots of 1 plus 3i cubed plus 17 lots of 1 plus 3i squared plus 12 lots of 1 plus 3i minus 10. And we want to show that that gives us 0. So we've got two lots of 1 to the 4 plus 4 lots of 1 cubed times 3i. So we're using our binomial expansion here, remembering from the first unit, plus 6 lots of 1 squared 3i squared plus 4 lots of 1 3i cubed plus 3i to the power of 4. And that's us just expanding the first bracket. Right? We haven't even tidied that up yet. So we're going to find that when we're dealing with these, the maths itself is not difficult. Right? It's just basic and simple arithmetic. There is just a lot of it. Okay, so 1 cubed plus 3 lots of 1 squared 3i. And you're going to find it takes several lines. That's going to be the thing that causes you the most upset. You're also going to find that because of the sheer volume of the arithmetic, you're going to make silly mistakes at times. Okay, and that's going to be the number one cause of you getting it wrong as you're working through it. 1 plus 2 lots of 1 3i plus 3i squared plus 12 plus 36i. Right, that one's a bit nicer. And we are hoping that that gets us 0. So we're hoping all our real parts and all our imaginary parts cancel out. So tidying it up, I've got in my first bracket, I've got 56 minus 192i. Okay, you're fortunate that I've already done this for you. We're not going to have to do it again. Minus, so we've got minus 78 minus 54i plus minus 192 136 plus 102i plus 2 plus 36i. And by the time we work our way through all of those things, we find that actually we are left with nothing. It all cancels out. And so from that, 1 plus 3i is a root. And therefore we've also got 1 minus 3i is a root. And we are remembering that is because they are conjugates. So what we are looking to do now though is now we need to find the rest of the roots. Okay, it wasn't enough just to prove that one happened. And so what have I got? How can I find it? Let's scroll up a wee bit more. So if I wanted to write it, we could write z minus my roots. So I've got 1 plus 3i z minus 1 minus 3i. So it becomes z minus the root. Remember when we used to ask you to do your synthetic division, if it was x minus a as your thing in your bracket, you would write a there, you'd multiply through by a. Okay, so whatever it was you were getting as your root, you stick it into the brackets as x minus it. Here, the letter that we're dealing with is z, so it becomes z minus the root. That's where this bit here comes from. What I'm going to do is I'm going to multiply that out, so I get z squared minus 1 plus 3i lots of z minus 1 minus 3i lots of z plus 1 plus 3i 1 minus 3i. Tidying that up, I'm going to get z squared minus 2z plus 10. Okay, those are my two roots multiplied out, tidied up together. What I'm going to do is I'm going to do something that we've seen before. I'm going to do a bit of algebraic division. Okay, and what I want to know is I'm going to divide this bit. In fact, no, I'm going to divide this thing we started with by my roots so far. Okay, and what that should do is that should give me the things that I'm left with. It should give me the roots that we're left with. So if you think about even just a simple case of 3 multiplied by 5 equals 15, what I've done is I've found some of my roots, okay, and I'm going to do 15, the thing I started with, divided by one of them, and that should give me the remaining bits. Okay, that's what we're thinking about. It's that kind of idea that we are using here. So z squared minus 2z plus 10 is going into 2z to the 4 minus 3z cubed plus 17z squared plus 12z minus 10. So first thing we're doing is we're always looking at the biggest power. How do I make that match that? Well, I need to multiply it by 2z squared. So 2z squared, that's what I'm multiplying by, and so I multiply all of this by 2z squared. So I get 2z to the 4 minus 4z cubed plus 20z squared. Okay, subtract what I've got, and that leaves me with z cubed minus 3z squared. I can bring my plus 12z down. Again, I'm still looking at the biggest term. How do I make z squared match z cubed? Well, I multiply it by z. So I've got z cubed minus 2z squared plus 10z. So again, we're going to subtract them, and we end up with minus 3z squared minus 2z squared, so that was just minus z squared plus 2z. I can bring this down to here. Again, how do I make the biggest term match? How do I make z squared match minus z squared? I just multiply it here by minus 1. And so I'm going to end up getting minus z squared minus 2z plus 10. And I subtract that, that gives me 0. Now remember, when we're doing your algebraic division, that is what I want. Okay? If that is not equal to 0, okay, mistakes have been made. Because it should divide exactly. And because it divides exactly, I should have no remainder left. And I'm just coming back up to this bit here. Alright? When I knew these two things multiplied to give me 15, I rearranged it to divide. If I did it and I got a remainder, that means it doesn't divide exactly. But I know it has to. Okay? That's what it is we're thinking about here. So, what I know is that my other factor has to be compiled of 2z squared plus z minus 1. Okay, this thing here on the top has to make it up. All I'm going to do is I'm going to factorise it. Make it equal to 0. And so I've got 2z minus 1, z plus 1 equals 0. And so that means z is equal to half, or z is equal to minus 1. Okay, when we're dealing with the numbers, there is nothing we can have as its conjugates because it's the imaginary part that changes. So what we would be thinking about here is a half plus 0i, or a half minus 0i. Well, actually, they make no difference, and so that's the same thing. We end up just having that. So these are my other two roots. This is a thing that we are often asked, but it's a very long and complex process. So you might want to stop, have a look back through this, and try and follow the steps now that we can see where the end goal might be. Okay, this is going to be one of these things that's going to take you a little bit of time. Again, you might want to watch through this as you are doing some. Okay, pausing it as you go. That's probably going to be one of the things that helps you. Okay,